when we use the rational zero theorem, there's a lot of trial and error involved. And when we have a really long list of possible rational zeros, it can feel a little bit overwhelming. So there are some theorems that give us some ways of strategizing about which possible rational zeros we might want to try first. The one I want to go over right now is Descartes' rule of signs. So it says, let f of x be a polynomial with real coefficients. So we are going to require that we have real coefficients. That's all we're working with this semester, but some of the theorems that we have allow for complex coefficients. This one does not. Okay. And a non-zero constant term. Okay. Now, that just means that if you have 0 as a constant term, there's some power of x that you can factor out first and then work with the remaining factor, which would have a non-zero constant term. If we've got a non-zero constant term, then the number 0 is not a 0 of the polynomial. Okay, so all of the real zeros that we have will therefore have to be either positive numbers or negative numbers. And this rule tells us something about how many positive ones and how many negative ones we could have. Okay. So it says here, the number of positive real zeros is going to be one of two things. It could be the number of sign changes in f of x written in descending order. Now, what does that mean? Well, let me give you an example. Let's suppose that f of x was x squared minus 5x plus 4. Okay, if I take a look, this is written in descending order. Now, that first term has a positive coefficient. This middle term has a negative coefficient, and this last term has a positive coefficient. Okay, so our terms go positive, negative, positive, looking at the signs of the coefficients. And if I'm plugging in a positive number for x, the sign of each term will match the sign of the coefficient. So if I plug in, for example, positive 2 squared is positive. Negative 5 times positive 2 is negative. 4, of course, is positive. So now I can look and I can say, that's where we change the signs. So there were two sign changes. So one possibility is that this could have two positive real zeros. The other possibility is that if it doesn't have 2, it's going to have less than that by some multiple of 2. So it couldn't have just one positive 0. It could have 2, or I could go down by 2. It could have none. Okay, those would be my two possibilities in this particular case. The second part of Descartes' rule of signs talks about the negative real zeros. Okay, so that says that could be either the number of sign changes in f of negative x. So I would plug in the opposite of x for x. Now if I do that with this particular example, let me just do that right here. F of the opposite of x would be the opposite of x squared minus 5 times the opposite of x plus 4. Now, that's just x squared. This is going to become plus 5x and then plus 4. All of those terms are positive. And notice, if I plug in a negative number, it will match these signs. If I were to plug in, let's say, just negative 1. Negative 1 squared would be positive. Negative 1 times negative 5 would be positive, and 4, of course, is positive. So, here, everything is positive. I have no sign changes. Oh, this has no negative real zeros. Now, this is a sort of silly example because this is quadratic, so I wouldn't be using the rational zero theorem for a quadratic. I would either just factor it by inspection, or I would use the quadratic formula. But if I use Descartes' rule of signs and I get that there are no sign changes in f of negative x, I know there are no negative zeros. So my list of possible rational zeros is cut in half. I don't need to try any of the negatives. Okay. So this can help you in strategizing for what possible rational zeros you want to try first. All right, what I'm going to do is just leave this up for just a second so that you can get it copied down. You may need to pause the video to get it copied down. That's totally fine. And then I want to talk about why this works. Okay, I didn't pause that for super long, but you've got the ability to pause the video. Let's just take a look at this example to see if we can understand why this is going to work. So if I'm looking for, well, let's actually write this in factored form. Notice this factors as x minus 4 times x minus 1. So it actually does have two positive zeros, because it would have a 0 at 1 and it would have a 0 at 4. Okay. So this is just going to be a parabola that opens up. And here are my two x-intercepts, would be the point 1, 0, and 4, 0. The zeros are the x values of those 1 and 4. Okay. Now, I mentioned that when we're plugging in something positive, okay, so I'm really just looking, if this is my number line, at numbers that are bigger than 0 here. When I plug in something positive, x squared will be positive. Negative 5x will be negative, and 4 will be positive. So the sign of what I get when I plug in a positive number will match the sign of each term. Okay. Now, I know that x squared determines the end behavior. We know that polynomials are going to be dominated by their lead terms. So I know that eventually we've got to be positive. So once we're far enough to the right, beyond, in this case it turns out beyond 4, then this term is really going to be dominating and we're going to have something that's positive. Okay. I also know that if I'm really close to 0, these two terms are going to be very small. So this is going to dominate. Okay. And that's essentially what happens here. From 0 to 1, this function is positive. Between 1 and 4, so on this number line, I'm just recording the sign of things. Between 1 and 4, this function is negative, and to the right of 4, this function is positive. And I understand why. Between 0 and 1, it's positive, because these guys are really small. This guy is really in control, and it's positive. Now, the x squared is helping it out a little bit, but really this term is dominating over this interval. Why is it negative? Well, the only way it could be negative is if this negative term has a bigger absolute value than these two positive terms combined. Okay. And that's going to happen between 1 and 4. So essentially, there's this interval where this guy is the dominant term. There's this interval where this is the dominant term, and there's this interval where this is the dominant term. So what happened is when the sign changed, each one of those pieces had something where it was the dominant, excuse me, it was the dominant part, excuse me, it was the dominant part, and therefore its sign dictated the sign of the entire polynomial. Okay, now, so that explains why the number of zeros can match the number of sign changes. Because essentially I'm saying this has a place where it's dominant, this does, and this does, but that means we're changing the sign twice. When we change sign, we do that at a 0. Okay, now let's suppose I looked at f of x equals x squared minus 5x plus 10. Now, I know what I'm doing there is I just added 6 to this. Okay. And so I'm just doing a vertical shift of this up 6 units. Now, if this vertex was less than 6 units down, that's going to translate this up so that we now have no zeros. In other words, I made this term big enough that this term is never going to be big enough to counterbalance these two terms trying to make it positive. Okay. And let's actually just double check that that does happen. If I were to calculate the vertex here, the x value of the vertex would be at 5 halves. The y value would be at 25 fourths minus 25 halves plus 10. That's 25 fourths minus 50 fourths plus 40 fourths. Yep, that's 15 fourths. That vertex is up here and it's opening up, so we've got no zeros. So what happened is by making this term so much bigger, we took away the power of this term. If we take away the power of this term so that it no longer got to dominate, we lose both sign changes. We lose both the passing from positive to negative and then passing back from negative to positive, and so we lose 2 zeros. Okay. So we go down by a multiple of 2. Okay. So that's an informal explanation of why that works for the positive zeros. Now, for the negative zeros, we're supposed to look at f of negative x. Now, we said this one, if I plug in negative x, we get no sign changes. Okay. But let's look at a slightly different polynomial. Let's look at g of x equals x squared plus 5x plus 4. Different polynomial, very similar. Notice this would be x plus 4 times x plus 1. I would have 2 zeros, and they're both negative. So I would have a 0 at negative 1 and at negative 4. So I'd have a parabola something like so. Okay. And now we're really looking at this part of our number line where this is 0, and we're looking at the negative numbers. Okay. And what's happening is to the left of negative 4, my polynomial is positive. Between negative 4 and negative 1, it's negative. And between negative 1 and 0, it's positive. Okay. Now, if I look at g of negative x, that would be negative x squared plus 5 times the opposite of x plus 4. That's x squared minus 5x plus 4. The reason I wanted to plug in that negative is because when I plug in a negative, some of my terms are going to have a sign that's different from the signs of these terms. When I plug in a negative to x squared, I'm still going to get something that's positive. When I plug in a negative to my constant term of 4, it's still going to be 4. I'm going to have a positive. But when I plug in a negative to 5x, it becomes negative. So by looking at g of negative x, now the signs of these terms match the signs that I'm going to get when I plug in a negative number. And I can see this is positive, this is negative, this is positive. That's 2 sign changes right there. And again, each time we have a sign change, that's essentially saying there's a section of the number line where this could be dominant. And I know that's going to be out here. The lead term determines the end behavior. There's a section of the number line where this is dominant. I know really close to 0, these guys are going to be super, super small, so the constant term is going to be dictating the sign of the polynomial. And there could be an interval in between where the negative 5x is dominant, and that makes the polynomial negative. So it's entirely possible, as we have here, that the number of negative zeros matches the number of sign changes. But once again, it would be possible if I were to change this to be x squared minus 5x plus 10, that I would lift this up so high that I basically take away that power of that middle term. It's never big enough so that the fact that it's negative brings the entire polynomial down. It's always going to be counterbalanced by these two guys working together to make it positive. And so if that happens, if this piece doesn't have an interval where it's in control so that we're always positive, we lose those 2 sign changes. So the maximum number of negative zeros we could have with 2 sign changes is 2. If we don't have that many, we always lose them in pairs, because we lose the change from positive to negative and the change back from negative to positive.